Hello everyone, this is part 3 video on past year NEET questions from the topic work, energy, power. We'll start with a question that has come in the year 2014. A body mass 4m is lying in the xy plane at rest. Means the initial momentum of this body will be equal to what? 0, because this is at rest. It suddenly explodes into 3 pieces, means it is breaking into 3 pieces. 2 pieces each having mass m move perpendicular to each other with equal speeds v, means both are moving, like say for example one of them is moving like this, other will be moving in the perpendicular directions. Okay, that is how they both are moving. What will be the third piece? See, each of them are having mass m, means third piece will have a mass 2m. Correct. The question is the total kinetic energy generated due to the explosion is. So we know the kinetic energy of one of them is what? Half into m into v square. Kinetic energy of the other is what? Half into m into v square. We need to find what is the kinetic energy of the third piece. For that, we will use the principle of conservation of momentum, because we know that both collision as well as explosion, right, they have to obey the conservation of momentum, because they are after all internal phenomena. When explosion is happening, right, this 4m is breaking down because of the internal phenomena. There is no external force. Means whatever is the initial momentum should be equal to final momentum. Means what? Final momentum of these 3 particles should add up to 0. Look at this. What is the momentum of the first particle? M into v towards, maybe we can say it as what? Positive x-axis. Second particle is what? M into v towards the positive y-axis. The resultant of them, right? What is the angle between them? 90, right? Resultant will be what? We'll get the resultant by using the vector resultant formula. So if you have two vectors a and b perpendicular, resultant is what? Root of a square plus b square, right? Which means what? Root of m square v square plus m square v square. That is what? Root 2 times of mv. That is the resultant. Now the third mass should exactly have the same momentum magnitude but opposite direction. Means what? The third mass momentum should be equal to what? Root 2 times mv. In terms of magnitude, direction wise it should be opposite. So what happens? This is like what? P1 plus P2, and when we add it to P3 it will be adding up to 0, because two vectors having equal magnitude opposite direction, they will add up to 0, which means the P3 value should be equal to what? Root 2 times mv. But that is what? If you say the velocity of this is, say for example, v dash. What is the momentum formula? Mass of the particle 2m into v dash, right? So you can see here m is cancelled, 2 will come to this side, so root 2 v by 2, that is what? V by root 2, that is our v dash. So the third particle velocity will be what? V by root 2. So kinetic energy of the third particle will be what? Half into its mass, which is 2m, into velocity square. What is it? V by root 2 the square. Means if you square it, means it will be what? V square by 2. So 2 we can cancel. Then what we'll have? We'll essentially have half mv square. So numerically the third particle kinetic energy is also what? Half mv square. They are asking what is the total kinetic energy generated due to the explosion. Means what? We have to add ke1, ke2 and ke3. What is it? Half mv square plus half mv square plus half mv square. What is the value? 3 by 2 mv square. So here, where is this kinetic energy basically coming from? It will come from the internal energy sources, maybe chemical form of energy or something due to the explosion, right? That will convert itself into the kinetic energy of the particles. Some amount of energy might even get dissipated in the form of light, heat, etc. also. We have seen quite a number of questions on this explosion. Next we have a question that has come in the 2013 paper. A uniform force which is given in newtons, 3I plus j, acts on a particle of mass 2 kg. Hence the particle is displaced from position 2I plus k meters to the position 4I plus 3j minus k meters. Work done by the force on the particle. See here what they are giving us. The initial position vector, what is it? 2i plus k. Final position vector, what is it? 4i plus 3j minus k. So what is the displacement vector? It is what? Final position vector minus initial position vector, right? What is it? 4i plus 3j minus k minus of 2i plus k. That is what? 2i plus 3j minus 2k. This is the displacement vector. Force is there, it's a uniform force. We need to find what is the work done by the force, right? For a constant force, what is the work dot product between the force vector and the displacement vector, right? So here, I mean, we are just representing it as delta s. We can even represent it as what? S bar. Because generally, you know, for a constant force, right, we will represent the formula like this. No, W is equal to F dot S. Okay, so we can even represent it with delta S. That's not a problem. So F is what? 3i plus j dot, what is the displacement vector? 2i plus 3j minus 2k. That's it. So dot product of two vectors is what? Product of the I component. Here it is what? 3. Here it is what? 2. So 3 into 2 plus product of the j component. Here it is 1. Here it is 3. So 1 into 3 plus product of the k components. Here there is no k component, right? Means 0. What is the k component there? Minus 2. Anyway, it will be 0 only. So what is it? 3 2s are 6. 1 3s are 3. Totally what is it? Since force is in Newton and displacement is in meter, work will be coming in terms of joules. So what is the answer for this? 9 joules. Now here one thing we have to be careful. Some of us, right, will try to force fit this mass somewhere, because mass doesn't come into picture, isn't it? Because work will be what? Depending upon the force vector and the displacement vector. So we should not force fit somewhere into the calculation the mass value. So that value is given just to sort of, you know, make some of us to think that, you know, where do we put this mass? So we should not be getting, I mean, you know, distracted by the additional information that will be given. Sometimes, you know, in problems, right, they can give some extra information which is not required to solve the particular problem. Okay, so we should only take what is required for us and then move on. Next we have a theoretical question. This has come in the Karnataka paper. A particle with a total energy E is moving in a potential energy region Ux. So you are talking about a region where the total energy of the particle is E and potential energy is what? Ux. Motion of the particle is restricted to this region when? See, when the motion of the particle will be restricted to the region, here, no, we need to understand one thing. Total energy will be equal to what? Potential energy plus kinetic energy. Now kinetic energy has got, for any moving particle, right, what is the kinetic energy? Half into mass of the particle times square of the velocity, right? Which means what? This will be always non-negative. It can be 0 also. When the velocity is 0 means it will be 0. It will be always what? Non-negative. This kinetic energy will be always non-negative. Which means what? If we are able to restrict the motion of the particle to the region, means what? If outside the region the kinetic energy takes values that are not allowed. If outside the region, we will define the region such a way that the condition of the region we have to define such a way that outside the region kinetic energy takes values that are not allowed. Means what? The motion of the particle will be restricted to this particular region only. So look at it. What is the condition we can think about it? If we look at inside the region, we will define the relation between the total energy and potential energy like this. So here what is the kinetic energy formula? E minus potential energy, right? This is the kinetic energy formula. We define our region such that the kinetic energy, right, will be always greater than or equal to 0. So which means outside the region, if the particle has to go, the region itself we are defining like what? Kinetic energy is always greater than or equal to 0. Means if outside the particle has to go, then it has to go to a condition where kinetic energy will be less than 0. means the particle will not be able to go to outside the region. So what is the condition will require? The region should be defined such a way that the kinetic energy is more than or equal to 0. So which means what? E minus potential energy is more than or equal to 0. That means from here what we can write? E will be more than or equal to potential energy, or we can also write it like this: potential energy is less than or equal to E. So which is our option C. If you define the region like this, right, then if at all the particle has to go outside, it has to go into the condition kinetic energy less than 0, right? But the particle cannot have this kinetic energy less than 0, means whatever the region we are defining, the particle motion will be restricted to this region itself. So clear? So what is the answer for this? It is option C. So we have a question that has come again in the Karnataka paper 2013. One coolie takes 1 minute to raise a suitcase through a height of 2 meters. But the second coolie takes 30 seconds to raise the same suitcase to the same height. Means what? We have a first coolie who is raising a suitcase to a height of 2 meters. Time taken in this case is 1 minute. Second coolie is raising the same suitcase to the same height, 2 meter. In this case, what is the time taken? 30 seconds. The powers of two coolies are in the ratio. See, where is this power concept coming from? Say for example, the suitcase is having a mass m. We are raising it through a height 2 meters. So what is the work done by the first coolie? Mass of suitcase into acceleration due to gravity into height. So this much work is done. So to lift it through a height of 2 meters, he will have to do work of mgh, right? Similarly, second coolie also, he is also raising the same suitcase through same height, which means in this case also work will be same. But what is the difference? In this case, the time is what? 1 minute means 60 seconds. Here time is what? 30 seconds. The difference is in terms of time. So look at this power will be what? M into G into 2 divided by, in this case, 60 seconds. Worked by the time taken. Power in the second case is what? M into G into 2 divided by what? 30 seconds. Now they're asking us what is the ratio of the powers, right? P1 by P2 is what they're asking, which is what? M into G into 2 divided by 60 seconds divided by M into G into 2 divided by 30 seconds. So M into G into 2 is common everywhere, that will get cancelled. 30 seconds will go to the numerator, so we'll have 30 seconds by 60 seconds. What is it? 1 by 2. So the ratio of the powers will be what? 1 by 2. It's a very standard result based question. If the work done is same in two cases and the time taken is different, then the ratio of the powers, right, will be equal to the inverse ratio of the times, because P1 will be equal to what? W by T1. P2 will be W by T2, right? W will cancel, it will get become what? T2 by T1 it will become. It's a very standard result. In both the cases, if the work is same, then the ratio of the powers will be equal to what? The inverse ratio of the times. Next we have a interesting question. Of late we are not seeing these kind of questions. This is based on the idea of what we call as a stable equilibrium. The potential energy of a particle in a force field. This is the potential energy function. What is the potential energy function? A by r square minus b by r, where a and b are positive constants. So a and b, both of them are what? Positive. R is the distance of the particle from the center of the field. Okay. For stable equilibrium, the distance of the particle is, means they are asking us what? For stable equilibrium, what is the value of R? That is the question they are asking. First of all, what is this stable equilibrium? Generally, when we talk about equilibrium, right, we have stable equilibrium and unstable equilibrium. There is one more type called as the neutral equilibrium, but we'll try to mainly focus on the stable and unstable. When we have the equilibrium, the potential energy function will be either attaining a minima or a maxima. When it is attaining minima, right, that is what will be the stable equilibrium. The place where it attains maxima will be the unstable equilibrium. Like generally the way we will try to visualize it is, if you think about a vessel and consider another inverted vessel. Now if we keep an object in this vessel over here, if we try to give some displacement to the object either this way or this way, what do we see? The object will try to come back to this equilibrium. Why? Because in this equilibrium position, right, it is having the potential energy minimum. If you try to move it, means we are taking it to a high energy, so it always tries to come back. So this is what will be the stable equilibrium example. And you look at this one, if you keep an object at the top, this is also at equilibrium initially, but if we displace it slightly, what is going to be observed? If we just displace it this way, means it will keep going down. If you displace it this way, means it will keep going down, which means what? This equilibrium we will be calling it as what? Unstable equilibrium. So in unstable equilibrium, the potential energy in this case, what we see is actually the maxima. So here they are asking us what? To find the point where we'll have the stable equilibrium. So here first thing is, yes, we need to understand the concept of stable equilibrium and then unstable equilibrium, but we should also know how do we actually approach it. So how do we find, because this is a bit of a math involved here. So how do we understand when a function, so this is like a function, how do we understand when a function will attain a maxima or minima? So whenever you have a function, this is a function in terms of r, right? Whenever a function has to achieve a maxima or minima, in both the cases, right, the derivative of the function with respect to variable, means in this case du by dr, this will become 0. The derivative should become what? 0. Like whenever a graph, think about it, a graph is attaining maxima. You see what is the slope here? Slope of the tangent will be what? 0. Similarly, when it is achieving minima, here also we see the slope of the tangent will be what? 0. So whenever a function is achieving maxima or minima, the derivative of the function with respect to the variable has to be 0. Now we are going to use that condition only. So here first step is what? To find when the derivative will actually become 0. So for that we should first find out what is the derivative. Du by dr we should find out. So we have to take a derivative of this. We can write it like what? A into r power minus 2 minus b into r power minus 1, like that we can write. So a is the constant, right? A into derivative of r power minus 2 minus b into derivative of r power minus 1. So this is like what? We have a standard derivative. Derivative of x power n will be what? N into x power n minus 1. So look at this, a into minus 2 r power minus 2 minus 1 minus b into minus 1 r power minus 1 minus 1. So what is it? Minus 2a into r power minus 3 plus b into r power minus 2. So we can also write it like minus 2a by r cube plus b by r square. So this is what is our derivative. Now we are saying this should become 0. When the function is reaching a maxima or minima, this should become 0, which means what? If we equate it to 0 means what we will get? 2a by r cube should be equal to what? B by r square. Now when we cancel, what we'll have, will be just left with r. So if you rearrange, means what? 2a by b, that is our r value. 2a by b is what? R. Now some people will try to conclude the answer from here itself. See, when the derivative is becoming 0, at what point the derivative is becoming 0? It is becoming 0 at r is equal to a by 3. Now derivative 0 means we can either have a potential energy becoming maxima or minima. So here Stable equilibrium means what? The potential energy should become minima, right? If we have two values coming, then we may have a confusion whether the function is going to become a maxima at which point and minima at which point, like that. But here we are only getting one value, means r is only coming as what? 2a by 3, right? And we see only one of the options matching here. What is it? Option B. So some people will try to conclude from here itself, saying at the point which is r is equal to a by 3, the function will be having the minimum potential energy, and hence there is a stable equilibrium. But what we'll do is we'll try to verify the other point also. So the first conclusion we are able to draw. What is it? Derivative is 0 at which point r is equal to 2a by 3. Now at this point, the function, potential energy function, may attain a maxima or may attain a minima. How do we know when it will attain a maxima or when it will attain a minima? For that, right, the second derivative, if the second derivative, or we call it as a double derivative, if the second derivative of the function is less than 0, negative, at that particular point the function will be what? Maxima. Okay. If the second derivative is positive, then at that point the function is minima. So generally we should not think negative means minima. So when the second derivative is negative, that is corresponding to what? Maxima. When the second derivative is positive, second derivative positive means what? Minima. Second derivative negative means what? Maxima. So we already have the derivative function, right? What is the derivative function? It is what? Minus 2a by r cube plus b by r square. This is the derivative function. We equated to 0 and got the r value as 2a by 3. But this is the derivative function, right? Let us talk about the second derivative. Second derivative means what? We have to take the derivative one more time. Means derivative of minus 2a by r cube plus the derivative of b by r square. So here minus 2a is a constant. This is like what? Derivative of r power minus 3. B is a constant. This is like derivative of r power minus 2. So minus 2a into same derivative exponent formula. Minus 3 into r power minus 4 becomes b into minus 2 r power minus 3. So if you look at it, what do we have? Minus into minus becomes plus. So 6a by r power 4 minus 2b by r cube. What is the second derivative? 6a by r power 4 minus 2b by r cube. So now what we are trying to do is we are trying to check whether really this r is equal to a by 3 point corresponds to the minimum or not. Okay. So this is the second derivative function, right? This is second derivative function. In this we have to substitute r is equal to 2a by 3. So substitute r is equal to a by 3. What do we have? 6a divided by r power 4 means what? 2a by b whole power 4 minus 2b by r cube means what? 2a by b whole cube. So look at this. This is like what? 2 power 4 means what? 2 power 4 is 16. So 6a by, maybe we'll just erase the other thing so that we can use the space to calculate. So now what we are trying to do is we are trying to validate whether this r is equal to 2a by b point, is it corresponding to the minima point for the potential energy or for the maxima point. What we already know what is the answer that we are going to get, right? What is the answer we are going to get? We will get the answer saying that at this point the minima will be achieved. Okay. So 6a by 16a power 4 divided by b power 4 minus 2b divided by, this is what? 2a by b whole cube, right? Which means what? 8a cube by b cube. So here the b cube will go to the numerator. Here 1a will get cancelled. B power 4 will go. So what is it? 6 by 16 means 3 by 8 b power 4 by a cube minus 2 1s are 2 4s are. Here also b power 4 by 4a cube. Now if we take an LCM of this, right, what do we get? If we take an LCM of it, it will be what? 8a cube will be the LCM. This is 3b power 4 minus 2b power 4. That will be what? b power 4 by 8a cube. And anyway, what they are saying, a and b are positive constants, which means what? This entire expression is going to be positive. Remember, if the second derivative is positive, here we are getting second derivative is what? Positive. If the second derivative is positive, means what? That corresponds to minima. So which means the r is equal to a by b point, right? That is going to correspond to what? The potential energy being minima. And when the potential energy is minima, that is what is our stable equilibrium. So what is the answer for this? The distance of the particle where the stable equilibrium is achieved is what? R is equal to 2a by 3, 2a by b. Okay. So here these kind of questions, right, they do involve little bit of calculation that is going to happen. But like I said, right, if we make the first derivative 0 and we get only one r value, generally in these kind of questions, right, we get only one r value. If you get only one r value, means probably from there itself we can conclude, unless we see an option saying that no, none of them or something like that. If there is a contradicting option like that, then we have to be careful. Otherwise, we are getting only one value for the r. Definitely that has to be the minima point, right? Unless we see an option saying none of them or something like that. Okay. So that is one way in which we can probably conclude the answer even without going for the second derivative. But the best thing is to go for the second derivative and check whether really that is the point corresponding to the minima or not. So for the stable equilibrium, potential energy function should be minimum. For the unstable equilibrium, potential energy function has to be maximum. Next we have a question. This is based on the conservation of energy principle. A solid cylinder of mass 3 kg is rolling on a horizontal surface with a velocity 4 meter per second. Now this rolling concept, right, probably we will be able to understand this better only after we complete this rotational motion. If you are somebody who is practicing this question before completing rotational motion, maybe you might want to skip this question. Why? Because here this is going to involve the understanding of the rolling of an object. Now this solid cylinder collides with a horizontal spring which is having a spring constant of 200 Newton per meter. The maximum compression produced in the spring will be, like, if you want to represent it like a diagrammatic manner, this is how it is. So we have the spring which is horizontal. Initially we assume that the spring is in the free state or the natural length. So we have a solid cylinder. We are looking at the side view. The solid cylinder is what? Rolling. Solid cylinder is basically what? Rolling. Okay. Now if you look at a object which is in rolling, right, the angular velocity and the velocity of the center of mass of the object. So here the 4 meter per second is what? The velocity with which the rolling body is moving forward. That is also what is called as velocity of center of mass of the rolling object. This v and angular velocity omega will have a relation. So if you consider that the radius of the cylinder is r, then v will be equal to r omega. The velocity of the center of mass will be equal to what? R omega. In case of pure rolling. In case of pure rolling, the v value will be equal to r omega. So this is how we'll have a relation between the center of mass velocity and the angular velocity of the body which is in pure rolling. This is something that we'll be learning about it in the rotational motion chapter. That is why I said this question probably we'll be able to understand once we complete that. Because a rolling object, right, will have two kinetic energies. One is the translational kinetic energy, which is half times mv square. Second is rotational kinetic energy, which is half I omega square. So this I is what? The moment of inertia. For a solid cylinder, right, which is rolling about its like you have a cylinder like this, it will be rolling about its axis like this. This is what we call as the principal axis. The moment of inertia of the solid cylinder with respect to principal axis will be mr square by 2. So I value will be what? Mr square by 2. So look at this. The rotation kinetic energy will be what? Half into I is what? Mr square by 2 into omega square. But you look at, from the rolling condition, right? R square omega square can be written as what? R omega the whole square, right? What is R omega V? Which means, what is it? This is like what? 1 by 2 into 1 by 2 is 1 by 4. 1 by 4 mv square. So this is the rotational kinetic energy. So the cylinder which is in rolling, right, will have both translation kinetic energy as well as rotational kinetic energy. What is the translation kinetic energy value? Half m v square. What is the rotational kinetic energy from this relation that we have discussed? 1 by 4 mv square it is coming. Okay, see, we have to keep in mind, it is not like always it is 1 by 4 mv square. It depends upon what is the moment of inertia of the object, etc. So here the total kinetic energy will be what? Half mv square translational plus 1 by 4 mv square rotational. Totally what is it? 3 by 4 mv square. So this is the kinetic energy of the solid cylinder as it is rolling and coming towards the spring. Now as it collides with the spring, what is going to happen? Like as after the collision, if the cylinder is rolling, means the spring is now going to get compressed. Now as the spring is getting compressed, understand what will happen. The spring will start developing potential energy, which is the spring potential energy. So look at this. When they say maximum compression produced in the spring, means what? The spring is not able to get compressed any further. So when we use the word maximum compression, right, which means what? After that we are not able to compress the spring anymore, which means what? The kinetic energy of this cylinder must become zero. If not, the cylinder will still keep moving forward and still keep compressing the spring. But when we say this is the maximum compression, means the cylinder is not able to compress the spring anymore, isn't it? Which means the kinetic energy of the cylinder is becoming what? Zero. Kinetic energy means we're talking about the total kinetic energy. Now where is this energy going? Initially the cylinder is having kinetic energy. In the final state there is no kinetic energy for the cylinder, right? What is happening? Spring is horizontal floor, same, the cylinder is also in the horizontal floor. So there is no change in the gravitational potential energy, no change. Gravitational potential energy change is not involved here. Why? Because it is all happening on the same horizontal floor, which means whatever the kinetic energy that is lost by the cylinder is going in the form of gain in the spring potential energy. So how much kinetic energy is lost by the cylinder when we talk about the maximum compression? This total value 3 by 4 into m is what? 3 into v square is what? 4 square. This much is the kinetic energy lost. Fully it is lost. Gain in the spring potential energy means what? If the spring is compressed by a value x, then the spring potential energy will be what? Half into k. K is what? 200 into the x square. That's it. So from here we will be able to get what is our x value. After this step, what is there? We'll just have to do the simplification and get what is the x value. Check it, what will be the x value here. So we have to see what all we can cancel. So for now what we'll do is we'll just leave this x square alone on the right hand side and let us try to bring everything to the, so here we'll cancel 2 1s are 2 100s are, we'll bring the 100 to the left side. So 3 into 3, here we can cancel 1 4 into 4 divided by 100 is equal to x square. Now we'll take a root on both sides. 3 into 3 into 4 can be written as what? 2 into 2 divided by 100 can be written as 10 into 10. So root of x square means what? X. LHS what is there? 3 into 3, one of them will come out. 2 into 2, one of them will come out. 10 into 10, one of them will come out. 6 by 10 means what? 0.6. Since everything is in the SI system, the x value must be in terms of the SI unit meter. So the maximum compression rate will happen when the cylinder is completely losing the kinetic energy and all of it is changed into the spring potential energy. Next we have a question based on the collision. Two spheres A and B, mass m1 and m2, they are colliding. A is at rest initially and B is moving with a velocity v. A is basically at rest and B is moving with a velocity v along the x-axis. Means what? If you keep the A here, which is at rest, B is like moving along the x-axis with a velocity v. So let us consider this as what? Positive x-axis. After collision, B has a velocity v by 2 in a direction perpendicular to the original direction. Means what? Once the collision is happening, B is going in a direction which is perpendicular to the original direction. Means original direction is x-axis. We took it as positive x-axis. After the collision, B will go perpendicular. Means here there can be two possibilities. One, B may go along the positive y-axis, or B may even go along the negative y-axis. That is the reason why I'll tell you in the end, right, this kind of question, right, can be even challenged. Because if you consider that the B is going along the positive y-axis, we will get a result. If you consider that B is going along the negative y-axis, because they are not saying whether it is positive or negative. What they are saying, after collision, B has a velocity v by 2 in a direction perpendicular to the original direction. Means positive y-axis is also perpendicular, negative y-axis is also perpendicular, right? So that is why these kind of questions, they can be challenged, because we'll see we are going to get two possible answers. So if, say for example, we assume that B is going along the positive y-axis, the mass A moves after collision in the direction. Means we have to comment on what is the direction in which the mass A will move. Let us say that A is moving in some direction like this. A is moving in a direction. This is the direction in which B is moving. We are taking it as what? Positive y-axis. Let us say A is moving in a direction making an angle with the x-axis, because if you look at the options, right, they are saying it will move in the same direction as B, or it will move in the opposite direction as B. And third and fourth options, they are saying making some angle with the x-axis. So what we'll do is we'll look at the general condition. What is it? This is what we have initially, B, A. So we'll take the mass of A as m1 and B as m2. That is what they are giving us. Before collision, this is at rest and this is only moving, which means before collision, what is the momentum along the x-axis? m2 into v. What is the momentum along the y-axis? 0. There is no component of velocity. Now let us look at after collision. So we are assuming that the B is anyway moving along the positive y-axis and A, we said, is moving along a direction making an angle theta. B velocity after collision is given v by 2. A velocity is not given. See, they are saying, asking us to find what is the direction in which A will move. So we will say v dash is the velocity of A after the collision. So here we are not interested much in this v dash value. We are interested more in this theta, because they are only asking about the direction part, right? Now look at this. The momentum of A, right, after collision will be what? m1 into v dash. We can take the components of this. How? The component along the positive x-axis will be what? m1 into v dash into cos theta. Along the positive axis, what is it? m1 into v dash into sin theta. What is the momentum of B after the collision? It is what? m2 into v by 2, that is also along the positive y-axis. Okay, now what is the momentum after the collision along the x-axis? B, momentum is fully along the y-axis, so only component is what? The component of momentum for the sphere A, which is what? m1 b dash cos theta. Now what is the y direction component? This is also y direction, this is also y direction, which means what? m1 v dash sin theta plus m2 into v by 2. Now collision, right? Total momentum must be conserved. Means what? These two should be equal. These two should be equal. Initially, whatever is the x component of the momentum should be equal to final x component momentum. So if we just equate them, right? Look at this. We can straight away call it as equation 1. Equation 2 is what? 0 is equal to m1 v dash sin theta plus m2 into v by 2. So what we'll do is we'll just bring this m2 into v by 2 to the left side. It will be what? Minus m2 into v by 2. That is equal to what? m1 v dash sin theta. Let us call it as equation 2. So we have two equations. Now we are not interested in knowing what is the v dash value. We are only interested in knowing what? The theta, because that is what is asked in this question. They are asking, in which direction the sphere A will actually move. Now what we do is let us just do equation 2 by equation 1. Means left hand side, what we'll have? Minus m2 v by 2 divided by m2 v. That will get cancelled. Right hand side is what? m1 v dash sin theta by m1 v dash cos theta. So m1 v dash is cancelled. So what we'll have? This is minus half is equal to sin theta by cos theta is what? Tan theta, which means theta is equal to tan inverse of minus half. Which means the theta, right? Tan inverse of minus half means what? The angle is negative. So in the diagram we are showing it like this. But theta value is what? It will be negative. Which means what? The A velocity will be aligned, making a negative angle with the x-axis. A velocity will be aligned, making a negative angle with the x-axis. So if you look at it, right, so this is the x-axis. This is what is the angle going to be. Because when you measure the angle on the other side, right, see this side you measure the angle means we'll take it positive. Other side we'll measure the angle means what? Angle is going to be what? Negative angle. So what is the angle? We'll say tan inverse of minus half with the x-axis. So look at it, what is the answer? Tan inverse of minus half to the x-axis. Okay. But as I said, this question can be challenged. How this question can be challenged? If instead of taking the velocity of B to be along the positive y-axis, if we would have taken the B to be moving along the negative y-axis, then what would happen? Exactly the A will be moving with the same angle in the opposite direction. Means previously we took B to be moving along the positive y-axis with a velocity v by 2 after collision. That's the reason why what is the conclusion we had? A will move like this, right? A will move making a negative angle with the x-axis. If we take the B itself to be moving along the negative axis, because in the question statement they have not mentioned whether the B is moving along the positive or negative. So they are just saying that B is perpendicular. Means we can take it as either positive or negative, right? If we take B to be going along the negative axis, then A will be exactly symmetrical. Instead of making an angle this side, it will make angle that side. And here what do we represent the angle as? Tan inverse of half, right? So in that case we will be saying that the angle made by the A velocity after collision will be what? Tan inverse of half with the x-axis. So we could be saying that option C is the answer. So which means because of the little ambiguity in the statement of the question, both C can be an answer as well as D also can be an answer. Okay, so here, but the basic approach is what? We are simply using conservation of momentum. So conservation of momentum along the x-axis, conservation of momentum along the y-axis. Next, we have a question from 2012 mains paper. A car of mass m starts from rest and accelerates so that the instantaneous power delivered to the car has a constant magnitude p naught. So car is starting from rest, means what? Initial velocity is 0. Is getting accelerated, means what? There is a force acting on it. The instantaneous power delivered to the car has a constant magnitude p naught. So here, because it is starting from rest and moving because of this force, the velocity must be in the same direction as the applied force. What is the instantaneous power? Means power acting on a particular object, moving object, will be what? F dot v, right? So since F and v will be in the same direction, it is what? F into v. This is constant, they are saying p naught. The instantaneous velocity of the car is proportional to, means if this is the case, we need to find what is the instantaneous velocity in relation to time and maybe mass. So look at this, what do we have? We have that F into v is p naught. But what is F? Mass times acceleration, right? Into v is equal to what? P naught. Acceleration can be expressed as what? dv by dt. If we rearrange, means what we'll get? M into v dv is equal to p naught into dt. Now here when we integrate this, right, we will be able to understand velocity, how is it changing? Initial velocity is 0. Let us say the velocity after time t is t. Time is starting from 0 to t. So from here we will be able to get the relation between the instantaneous velocity and the time. So look at this, m is a constant, right? Integral v dv is what? It's like integral x dx. What is this? X square by 2, which is v square by 2 minus 0 square by 2. Final limit value minus initial limit value. Here p naught is a constant, right? Integral dt means what? What is integral dx x? Here also we have to substitute the limits. Final limit is t, initial limit is 0. So look at this, what do we have? M into v square by 2 is equal to p naught into t. Now if you take everything to the other side, v square will be what? 2 p naught t by m, which means v is equal to what? Root 2 p naught t by m. So what is the relation that we have? The instantaneous velocity, right? We can see it is proportional to what? T power half. The instantaneous velocity is proportional to t power half. It's a very standard question. Option B is the right answer. So here all that we are doing is looking at the power relation with force and velocity, expressing acceleration as dv by dt, then integrating it. Next we have another theoretical question. The potential energy of a system increases if work is done upon the system by a non-conservative force, by the system against a conservative force, by the system against a non-conservative force, upon the system by a conservative force. Like what is this whole mess about conservative and non-conservative? Because the way we read it, it might be a little bit confusing. Let us understand what is it that we need to achieve. The potential energy of the system should increase. That is the objective, right? Potential energy of the system should be increasing. Now, what is the work energy theorem statement? Work done by the other external forces and non-conservative forces. Work done by the external forces and non-conservative forces will be equal to change in kinetic energy plus change in potential energy. Okay, now first option is what? If work is done upon the system by a non-conservative force. If work is done upon the system by a non-conservative force means this will be having a positive value. Now this has a positive value does not mean that the potential energy will be increasing, because there is also kinetic energy term, right? There is a kinetic energy term, there is a potential energy term. So just because an external force or a non-conservative force is doing work on the system does not mean that the potential energy has to increase. So we cannot say clearly. Let us look at option C. The work is done by the system against a non-conservative force. In that case, you know, this W will be what? Negative. Here also, we will not be able to see clearly what is going to happen to the change in potential energy. We will not be able to say whether this is going to be positive or this is going to be negative. Our objective is to see that this is positive. Our objective is to see that this is going to be positive. Now let us talk about the relation between work done by the conservative forces and potential energy term, because the way we define the potential energy term is work done by the corresponding conservative force is equal to what? Negative of change in potential energy. This is how we will define the potential energy term for any conservative force. Now look at it. If this work done by the conservative force is negative, then it means what? Negative negative will be cancelled, so that delta PE will be what? Positive. Work done by the conservative force negative means what? If I have to say work done by the conservative force upon a system negative, the other way to tell it is work is done by the system against a conservative force. So if I have to say that, the conservative force is doing a work of minus 20 joules, we can say it like what? The system is doing 20 joules against the conservative force, isn't it? So what is the correct answer for this? We need to have work done by the conservative force negative, then the corresponding potential energy change will be positive, means potential energy is increasing. So for that, what is the appropriate statement among the four options? The appropriate statement is work is done by the system against a conservative force. So previously we have cancelled this A and C. What about D? Look at it. Work is done upon the system by the conservative force. No. So here what is our requirement? We should have work done by the conservative force upon the system coming negative. But generally when we say D, right, this is actually telling about the conservative force doing some positive work. That is not what we are requiring here. What are we requiring here? The work done by the conservative force on the system negative. In other way, the system itself is doing work against the conservative force. So the correct statement is what? Option B. Next we have another theoretical question. This has come in the year 2011. A body is projected vertically from the earth, reaches a height equal to the earth's radius before returning to the earth. The power exerted by the gravitational force is greatest. So look at it, we have the object which is projected from the earth. So from here it is going to a height which is equal to the radius of the earth, and then it starts coming back. Okay. Now we need to comment on when the power exerted by the gravitational force is greatest. So what is the power formula? F dot V, right? Power formula will be at F dot V. And we know that as the particle is going away from the surface of the earth, force will be decreasing. As the body moves away, force decreases. And as the body moves away, see, finally the velocity is becoming zero somewhere. Means what? The velocity is also decreasing, right? As the body is moving away, velocity is also decreasing. Which means what? Power, we are saying, is the dot product between the force and the velocity. If both of them are decreasing, means what? We'll see that as the particle is going above, the power will keep on decreasing, right? But look at here, no. At the time of projection, as well as when it returns back, at the time of projection as well as when it returns back, it will have the same velocity, let's say v naught, but in opposite directions. At the time of projection it will be up, when it is coming down it will be v naught down. What about the gravitational force? It will be always acting down. Means at the time of projection, what will be the power? Dot product, right? Both the vectors are in opposite direction. It is velocity is up and force is down. So it will be what? F dot v means what? F into v into cos 180, which is F naught into v naught into cos 180 is minus 1. When it is returning to the ground, at the instant when it reaches the ground, now look at the power. Here the velocity is down, force is also down, which means what? It will be F naught into v naught. So the power, they are asking when it will be highest or greatest. When it will be highest? At the instant just before the body is hitting the earth. Now as it is going upright, what is going to happen? The gravitational force value is decreasing in terms of value, and velocity is also decreasing. It becomes zero, velocity becomes zero here, then it returns. When it is coming back and just about to hit the earth, right, that's when its velocity will be maximum in terms of value, force will be maximum, and both are in the same direction. That is when we'll have the maximum power. That is what? F naught into v naught. F naught is what? The gravitational force on the surface, and v naught is the velocity value. That will be value wise, it will be same both at the time of projection as well as when it is coming back and about to hit the earth. Now you might have a question, why the power is not maximum at the time of projection? See, value wise it will be what? F naught v naught, but it will be negative. Why it will be negative? Because the direction of the force and velocity are in opposite directions. That's why the power will be negative there. They are asking greatest power, right? So we'll have to take the positive value. So this is about this part video, and we'll see in the next part.